Hello there, Mr. Sutton here, bringing you the Algebra 2 3-6 lesson on quadratic inequalities. This is going to be a two-parter. In this one, we're going to be graphing inequalities and systems of inequalities in two variables. That'll be in part 1. In part 2, we're going to check out some inequalities in one variable. To start things off, we're going to do a little bit of a review of graphing inequalities in two dimensions, just with a line here. This is a linear inequality. So pause the video and see if you can fill in the blanks here and then graph what you see here. All right, let's see how that went. So when we're talking about an equals, like less than or equals or greater than or equals, any of those, that's going to give us a solid line and also any solid dots that you want to draw to help you graph it. If you don't have the equals, less than or greater than, either of those, then you're going to end up with an open dot, and a dashed line is kind of the equivalent of that. Now we can also talk about what direction we're shading. If we have y less than, that means we're going to shade everything lower than or below whatever the curve is that we just drew. And y greater than means we're going to shade above. Now if this were x less than, we would go left, x greater than, we would go right. So it's all about the positive or negative directions on whatever variable you're talking about. So now for graphing out this y greater than x plus 1, first we're going to just graph the shape itself, which is this line. This is kind of like graphing y equals x plus 1. So since this is in y-intercept form, or slope-intercept form, we can graph the y-intercept first, which is 1 right here. That's the b value for mx plus b form. So at 0, 1, we have a point, and since there's no equals under this inequality, that is going to be an open dot to represent that. Next up, this x here, we really have a 1x, so that's a slope of 1. So starting at our y-intercept, we go up 1, right 1, and there's another open dot. And then we do a dashed line through those. That's just an infinite number of open dots, essentially. And then to decide what direction we're going to be shading this, since this is y greater than, we're going to shade above. So everything above the line, like so. And this is the solution to a two-dimensional inequality. So one way you can figure out the shading is with the whole above versus below thing. But if you're ever confused, there's another way to do this. You can also test a point to check and make sure you're actually shading the correct side. So I usually pick an easy point like 0, 0. As long as it's not a point that's on the line or curve itself, it'll work out well. And if 0, 0 is on your line or curve, pick a different point like 1, 1. But the idea is you plug this point into your inequality and then just see if it comes out true or not and base your decision off of that. So we've got 0 for y, and 0 plus 1 is what I would write, plugging in the x value of 0. And I'm just asking, is 0 greater than 0 plus 1? Does 0, 0 make this true? 0 is not greater than 1. This is false. So that means we would not shade the region that had 0, 0 in it. And looking at what we did here, we did not shade that area. We shaded the other side. So we're good. So our first non-warm-up example is going to be to graph the inequality y less than negative x squared minus 2x minus 1. So at this point in the game, you've probably already graphed a whole bunch of parabolas in standard form and whatever other form. This is really the same process. The only difference here is that you're going to have possibly open dots instead of solid dots for your kind of guiding dots. And you might also have a dashed line instead of a solid line. It could be solid, though. You just have to look at the inequality. So dashed versus solid is one thing, and also keeping in mind shading above versus below. So really just applying all of that to a shape that you've been graphing for a while. So pause the video and see if you can take what you already know about graphing parabolas to kind of connect the dots and graph this thing. All right, so this is in standard form, which means I'm going to start using my vertex formula, negative b over 2a. So that's going to give me the x value of my vertex. We have then negative 2 over 2 times negative 1. That's going to be positive 2 over negative 2, which comes out to negative 1. Plugging that in for x to get the y value of the vertex, we've got negative 1 squared, which is going to give us negative 1 because we have 3 negatives there. And then this is going to be a plus 2. Negative 1 plus 2 is going to be 1. And then we have 1 minus 1, which gives us 0. So that then is going to give us a vertex of negative 1 comma 0, which I can put on my graph. So that's going to be negative 1, 0 right there. And again, open dots if you have no equals here. So next up, we're going to find the y-intercept. That's another easy point to find for standard form. That's just this negative 1 right here. So we have another open dot on 0 comma negative 1. And to get our third point using this standard form, we always like to do our axis of symmetry trick. So we'll just reflect the y-intercept over the axis of symmetry to get this negative 2 comma negative 1 point right here. And then through the open dots, again, since there's no equals, we're going to be doing a dashed line, a dashed parabola. And we have to figure out whether we're shading above or below. Y less than means we're shading lower than, so below. So that's everything underneath the parabola. And there's our solution. Now, one thing you want to be careful about with parabolas is that some people kind of get this notion in their heads that it's like an inside versus outside sort of thing, but it's not. It doesn't matter whether you shade inside or outside the parabola. All we're really looking at is whether you're shading above or below the parabola, whichever direction it's facing. For our next example, we're going to get a real-life application of quadratic inequalities. So let's say we have a manila rope, like this one here, used for rappelling down a cliff, and we're told that this can safely support a weight W provided that this inequality is satisfied, where D is the diameter in inches of the rope. So we want to graph this inequality and then interpret the solution. Okay, so to graph this, we're going to go to Desmos. And when I graph this, I can't just use W and D in Desmos. Desmos likes things in terms of Y and X. So here's Desmos. We're going to do Y. And for inequalities, you actually can graph these on Desmos. Let me just get to my home screen here. You can graph these on Desmos. So you would do less than and then press equals, and that'll give you less than or equals. You could just do less than without the equals, but let's try to do it like they have here. We'll do 140, and again, I can't do D. I'm going to have to use X. So 140x and then exponent squared. And there's my inequality, and it's not really a whole lot to look at. But you might see that there's a tiny little sliver in here where this parabola, it kind of opens up a bit. So we're going to adjust the scale a little bit so that we can make heads and tails of this thing. So let me make my x-axis a little tighter here. So I'm going to go from -1. I mean, I don't really need negative diameters anyway. What does that even mean? And then we'll just go to, I don't know, let's go to +3. Right? This is going pretty steep. So now we can see a little bit more of our parabola. Now, since this is so steep, we can also adjust our y-axis scale. Instead of going from -8 to 8, let me go from -8 to 80. Let's just increase that by a factor of 10. So now I can see a little bit better. Let me make that 800. How about 8,000? Right? So we can keep going until we have a good picture of this parabola. So this is essentially what this inequality is looking like. We have a parabola with everything underneath it shaded. So here's kind of a rough graph of what we just saw there. Now they wanted us to interpret the solution. So what do all these shaded points here actually represent? Well, the horizontal is the diameters, the vertical is the weights that those diameters can support. So this is basically all the weights that different diameters can support, all the weights that each thickness can support. If you're in the shaded region, for example, if you have a diameter of 2 inches, then that means you can support all these different weights. So you could go, 4,000, possibly a little bit less than 6,000. But boy, if you go to 7,000, you're probably going to have a rope that's snapping. So that's what all this is representing. On this example, we have now a system of inequalities here. And This could be a quadratic and another quadratic like we have here, or there could be a line mixed in there. It doesn't really matter. It counts as nonlinear as long as there's at least one nonlinear inequality in there. So how do we find the solution to a system of inequalities? Well, each inequality that we graph out is going to give us some kind of shaded region once we fully graph it out. The solution to a system is just going to be where those inequalities and their shadings overlap. So there will be some shaded areas that only apply to one or the other of these, and there will be some that they have in common. So really we just have to graph both out separately and then maybe shade a little darker where those shadings overlap. Pause the video and see if you can do this. Alright, so we'll do one at a time. These are both in more or less standard form, so let's just treat them both that way. The first one, our vertex using negative b over 2a. We've got negative, well that's a 0 for the b value, over 2 times negative 1. So that's just going to come out to 0. And then plugging that back in, we have negative 0 squared plus 3, which is just 3. So that was not so bad. That gives us a vertex of 0, 3. Since there's no equals on this inequality, I'm going to use an open dot and a dashed line when I graph all this. So we are here at 0, 3. There we go. Now this does kind of stray from our script for standard form a little bit because our vertex is also the y-intercept, so we don't have that easy extra point with the y-intercept that we can just use because they're the same thing. So we'll just plug in another x value that's pretty close to this, such as 1, and that'll give us another point that we can work with. So let me do negative 1 squared plus 3, and there's nothing magic about 1, it's just an easy number to plug in. So this is negative 1 plus 3, or 2. So that gives us the point 1, 2 right there. And then I can just reflect that over my axis of symmetry to get my third point at negative 1, 2. And then a dashed line through those open dots. Since we have y less than, that means we're going to shade below that parabola. So everything underneath there gets a shading. And we move on to the next one. It's really just kind of two separate problems lumped into one. So this next one is more standard for me than the first one was. We have that b value that we can see in there. So we have negative 2 over 2 times 1 for this one. So that's negative 2 over 2, or negative 1. And then plugging that in here, we have negative 1 squared plus 2 times negative 1 minus 3. That's 1 minus 2, which is negative 1, minus another 3 gives us negative 4. So we have our vertex at negative 1, negative 4. So we have a equals here for this inequality, so I'm going to use a solid dot and solid lines to represent this one. So we're going negative 4, or negative 1, negative 4, solid dot right there. We have a y-intercept of negative 3 that's different from the vertex, so I can put that on there. 0, negative 3 right there. And then reflecting that, we get negative 2, negative 3. Solid line through solid dots. There is our second parabola. And this one we were shading, let's see, we have a greater than, so we're going to shade above the parabola. So that's everything up here. Again, it's not inside versus outside, it's above versus below. And just as our final sort of answer here, we're just going to shade this overlapping region a little bit darker, and that overlapping region is actually the solution to this thing. Now, you could check your answer using a point. So if I plug in 0, 0, which is in here, is 0 less than negative 0 squared plus 3? Why, yes it is. 0 is less than 3. And is 0 greater than, this would just be negative 3 if I plug in 0 over there. Yes, 0 is greater than negative 3. So our point that we tested would verify that this is the correct region. So this brings us to the end of part 1. We're done with the two variable inequalities, and we're going to be moving on to one variable, and we'll see how that goes. So feel free to pause the video, do whatever in between practice problems you need to do, and then join us again later on. Welcome back. You're joining us for part 2 of quadratic inequalities. In this one, we will be doing all things one variable related. So our opening example is we've got x squared minus 3x minus 4 less than 0. Notice we only have one type of variable, just x here. So how do we do one of these? First thing we're going to do is basically figure out the zeros. If we're trying to figure out where this thing is less than 0, it would be nice to know where this thing is exactly 0. So that'll be our first step in the process, is we're going to find and then plot those roots on a number line. So pause the video and see if you can figure out the roots, and then we'll go from there. Alright, so if I'm figuring out roots for this thing, I'm going to pretend for a little bit that this less than is actually an equals. And I'm just going to solve this like I normally would, using factoring, quadratic formula, whatever I need to use. This one looks pretty factorable, so I'm just looking for things that multiply to -4 and add up to -3. 1 and -4 does the job, so we have x plus 1 and x minus 4 equals 0. And then that means that I have x values of -1 and +4. Alright, so I've got my roots, we just found them. What do I do with those? So next, those are going on a number line. So here's my number line, and I'm going to put these as dots on here. Now the type of dots I'm going to use, I have to be ready from the very beginning. Since we're dealing with inequalities, remember that dots can either be solid or open, depending on the type of inequality. Since this is no equals, that means we're going to have to use open dots for these. If there had been an equals here, we would have used solid dots. So at -1, I'm putting an open dot, and I'll label it with a little -1, and I'll put another open dot at 4. So there's no need to really label every single grid line here, as long as you label the dots that you do put on there and you write them in the correct order. Alright, so where do we go from here? So at this point we're going to do something called sign analysis, which is a highly useful technique that extends well beyond just this quadratic stuff. You can use this on polynomials or really anything else. The basic idea is that when we put these zeros on here, we divided this number line up into 1, 2, 3 different regions, or however many we divide it up into. We are going to plug in a sample number from each of these regions to see if it makes this whole expression positive or negative. We're going to do some sign analysis. Now I do recommend when you're doing this, if it's available, use a factored expression, because then when you plug in different x values, you can just quickly see, okay, am I multiplying 2 negatives, 2 positives, a negative and a positive? So that makes your sign analysis go a lot faster. So plug in some sample numbers, one sample number from each region, see if it makes this region positive or negative, and then just shade the regions that have the desired sign on them. And then write the inequality to describe that. So once you figure out whether these are positive or negative, take a look and see which one you actually wanted. Up here in the beginning it says less than 0, so you're going to want the negative areas on this particular problem. Shade those and then write an inequality that describes what's going on. So I know that's a lot, but pause the video and see if you can figure out the way of it, and then we'll bring it back and show you how I did this. Alright, so I'm going to pick some sample numbers from each area. I just need something to the left of -1. I think -2 works just fine. So I'm going to be plugging -2 into this factored expression. I've got -2 plus 1, which is a negative, and -2 minus 4, which is another negative. A negative times a negative gives me a positive. Notice that I don't care exactly what this comes out to, just whether it's positive or negative. So let's do another one. Between -1 and 4, I think 0 is the easiest number in there. 0 plus 1 is positive. 0 minus 4 is negative. Positive times a negative gives us a negative. Finally, something bigger than 4. I went with 5, but you could go with a million if you wanted. Anything over here will give you the same results. That was kind of the idea. So we have 5 plus 1 is positive. 5 minus 4 is positive. Positive times a positive is a positive. And there you have it. So now we said that we wanted less than 0, so we're going to shade the parts that we said were negative. So that's going to be this area between -1 and 4. And for an inequality that would describe this, well, we could say that x is greater than -1 and x is less than 4, Or to say that a little bit more succinctly, we could say -1 less than x less than 4, and that's just a faster way of writing one of those and statements. Now, if I had shaded the regions over here on the left and over here on the right, then I would have written x is less than -1 or x is greater than 4. So you need or when you have kind of a split area. For this next problem, we're going to do essentially the same thing we did on the last example, except we're going to use technology to give us a little bit of help. So we're solving this inequality by graphing with Desmos to help us. The first thing we're going to do on this one is graph the expression as a two-dimensional parabola. So that's going to help us find the zeros. So we'll do that together. So here is Desmos, and let me just move that so I can see. There we go. So we've got 3x squared minus x minus 5. So there's my parabola. So let me zoom in a little bit, and this will help me get my zeros now. So we have 1 there and 1 there. So -1.14 and 1.47. Beautiful. Let me just redraw that picture so you can all see it. All right. So once we've got those, we're going to plot our x-intercepts on a number line. Now, since we have the equals here, these are going to be solid dots. And by the way, you don't need to draw one of these number lines each time, but I'm just kind of including this to kind of give you the visual. You can do everything we're doing just by looking at the picture on Desmos. But here's what it looks like on a number line, just to kind of connect it to what we did before. So we had a solid dot at -1.14, and we're just approximating that, and a solid dot at 1.47. Now, for the sign analysis piece of this, we're going to perform our sign analysis just like we did before, but we're not going to just plug in sample numbers anymore. We're just going to look at whether the parabola that we graphed on Desmos is either above or below the x-axis. That will tell us whether we are positive or negative. So pause the video and see if you can do that, and then write the inequality that would best fit this situation. All right, so taking a look to the left of -1.14-ish, our parabola is above the x-axis, so that means that this expression is positive for those x values. In between -1.14 and 1.47, the parabola is below the x-axis, so we are negative in there. And then after 1.47, we're above again, so positive. Now, the inequality in the beginning said greater than or equal to 0, so we want these positive areas shaded here, or at least acknowledged. And then the inequality that would describe this, again, since we're splitting, we need an or statement, so we would have x less than or equal to -1.14, or x greater than or equal to 1.47. Now, there is something neat you can do just to check your answer on Desmos. So if we go back there, you can actually put this inequality in Desmos directly. So we can do greater than equals and then 0. And we can see that all this stuff that's outside of those two values got shaded in. And it's kind of hard to see unless you zoom out a bit and adjust the scale. But this is a parabola giving you everything below it shaded. For our final boss battle example, we have an archaeologist roping off a rectangular region of land to dig for some artifacts. The region has to have a perimeter of 440 feet, probably because that's the rope that they brought, that's how long it is, and an area of at least 8,000 square feet. So we want to just describe the possible lengths of this archaeological region. So essentially, we're going to have a range of lengths. We're going to need an inequality for this. So let's start with a little bit of geometry to kind of organize the information that they've given us. We're talking about perimeter and area of rectangles. So what's the formula for the perimeter of a rectangle? Well, that's going to be 2 times the width plus 2 times the length. So we have a nice little rectangle that this picture is here. So that's our P, 2W plus 2L. And we can be a little bit more specific for this problem. They said we must have a perimeter of 440 feet. Not less, not more, exactly 440. So we'll replace P with 440. Now they also said we had an area of at least 8,000. Area of a rectangle, you might remember, is length times width, or width times length. It doesn't really matter the order there. And they said that had to be at least 8,000. So greater than or equal to 8,000. So these are our two sort of, not equations, one's an inequality, but two pieces of information. So how can we kind of put all this together and solve for the length? Well, if we're solving for the length, it would be helpful if we didn't have the width in there kind of gumming up the works. So this is in part a system of equations inequalities sort of problem where we need to swap out the W for something that only has L's in it. So once you can do that, you'll have just a single inequality that has only L's in it. So pause the video and see if you can figure out how to approach this. Remember, you've got a substitution method works really well here, or you might be able to get elimination to work, but probably not. So pause the video, give that a shot, and then you can use technology to solve that quadratic inequality to get our final answer for these possible lengths. All right, if I'm going to get rid of the w's, that means I need to isolate the w in this first equation. So I can do that by subtracting 2L from both sides, and then dividing both sides by 2 to get the w alone. So that gives me w equals 220 minus 1L. And now I can replace w with 220 minus L in this inequality over here. So this can be rewritten as L times 220 minus L. And then let's see here, we've got, if we distribute that, that's going to be 220L minus L squared greater than or equal to 8,000. And then just going one step further to make this a little bit easier to graph on Desmos, let me subtract 8,000 from both sides. So that'll give me negative L squared, if I write this in decreasing order, plus 220L minus 8,000 greater than or equal to 0. All right, to Desmos we go to graph this. So we've got negative x squared. I have to use x's instead of l's here, plus 220x minus 8,000. And as is typical with these real-life problems, my initial screen doesn't really show me what I need here. So let me zoom out a bit until I see something. And probably we're looking for positive values. There's part of the graph. And if I go a little bit over, there's the other piece. Let me just adjust my y scale so it looks a little bit nicer. So let me make my y values go up by a little bit more. So 700. Does that show me what I need? No. I want to see the top here. So let me go to 7,000. There we go. All right. So there is what our parabola looks like. And the most important piece of this, again, is going to be the x-intercepts. So we have one right there at about 45.97 and another one here at 174.03. And we just want to note that as we go between those, the parabola is above the x-axis. So there they are again. Since I was looking for greater than or equal to 0 with this inequality, I want the parts where the parabola is above the x-axis. That's everything that we saw in between these values. So I can write 45.97, or however much I want to round that, less than or equal to L, less than or equal to 174.0 or 03. And that'll do it. So that's it for this one. Although this was a lesson on inequalities, hopefully you found yourself equal to the task. Till next time, Mr. Sutton signing off.